Just click the present and then submit.
I'm sorry, doctor. It says that I already sent my answer.
Yes, if you submit,
Me too.
if you send it once, then it's fine, right?
I didn't send it.
Yes, I didn't send.
You didn't send?
Me too, Mr.
Me too. Maybe it's the same one as yesterday. The same
Okay. Go ahead and do it now.
Do what?
Do again. Click on the link. Submit your response.
Doctor, where I can find the link?
The link is in the chat box, in the chat room. How are you guys seeing it? I don't know the student view. So just explain to him how he can access it.
On the meeting chat.
Okay, so okay, are you done with the attendance now?
Yes.
Yes, done.
Okay, don't duplicate your errors. Okay, so once you submit, standardized. Okay, so length is the distance between 2 points. When you are measuring the distance between any 2 points, that is called length, and the unit of that is meter. Right? In general, when we are talking about the meters, we are talking about relatively shorter distances. But as I given you this example in yesterday's class, that if I ask you what is the distance between your home and this university, most probably your answer will come out in kilometers. You might be saying 20 kilometers, 30 kilometers, or 100 kilometers. So you know that the meter is the unit of length, but we commonly use kilometers in our daily language, right? But other times when we're talking about very short distances, for example, you are having a ruler and you are sketching a line on your notebook, then in that point you are concerned about centimeters, because the meter in that hand is a little larger unit. So you don't use the meter in that, but rather you use centimeter. So it depends on the context and the things that we want to measure. So we change the units or the prefixes of that accordingly. So 1 kilometer is equal to 1,000 meter, and also 100 centimeters are equal to 1 meter. How the entire world started to know the length of the meter is actually this much, and it should be standardized. Okay, so what happened that there was, as I mentioned, that there were a lot of unit systems, and there were a lot of disagreements between people, like how to measure things. Some people would use the yards and the foot and other kind of units. And then there was another system which was parallelly running, which was using meter. So in order to standardize that, what the System International did, that they picked up this meter length, and it was just an arbitrary rod, okay? And that arbitrary rod they take, and they are saying that, okay, if this is the rod, then I will be picking up and calling it meter. But the story of this goes in this way. In 1792, the meter was defined as 1/1,000,000th of the distance from the North Pole to the equator of the Earth, okay? So in that way, that was, if you take the total distance and divide it by 1,000,000, the distance which you get, it will be called 1 meter. That was the first initial start of the this thing. Later on, the meter was defined as the distance between two finely graved lines near the end of a standard platinum iridium bar and the standard meter bar, like what we currently know it. Okay, the bar is placed in the International Bureau of Weights and Measurements near Paris, France. So what they did, they actually said, well, yes, it is from the North Pole to the equator, and if I have that distance divided by 1,000,000, then that will be 1 meter. But how can I tell people that this is 1 meter? So for that purpose, they had to pick something reasonably okay to be carried around the world. So they picked up this platinum iridium bar, and then they called this 1 meter. And then they started to match up other bars with it. and then they started to distribute those standard bars around the world. Okay, and then asked the other governments to print out more bars equal to this. So that's how people started to know that this is meter. But their definitions, which I said for the distance from the North Pole to the equator and divided by 1 million, that definition is extremely classical definition. So afterward, people were not really happy about that kind of definition. They wanted something more accurate with a high level of precision. So in 1960, the meter was defined to be if 1,650,763.73 wavelengths of a particular orange-red lines emitted by krypton 86 was discharged, then it will be called 1 meter. Okay, so since we know that the wavelength is kind of graphically represented, that it is moving up and down with the trough and valleys. If you have that many wavelengths, like as it is mentioned there, that is emitted by krypton 86, then the total length covered by that wavelength will be equal to 1 meter. That was a little bit sophisticated definition for it, and with a high accuracy. But later on, you know that when the Einstein General Theory of Relativity, since it was published in 1905, but later on it became extremely popular at the end of that century. So people wanted to associate the length of the meter with the speed of the light. So we know that the speed of light, as we are writing it, is 2.99 times 10 to the power 8 meters per second. Yes, it is. But if we go with a little more accuracy, then we are seeing even more significant figures. We know that here, that if I have, for some reason, I'm looking for the laser pointer, which is not coming up. I'm looking for this laser pointer. Anyway, that's a little bit troublesome. Something is okay. So we know that this is the speed of light, which is 299,792,000 and then 458 meters per second. This is the speed of light. So that many meters the light covers in 1 second. So what will be the meter then? Well, if the speed of the light is such that as it is given, if you divide 1 second by this number, so it will be a fraction of a second now. If the light cover distance in that much fraction of a second, that will be called meter. So this was the finally standardized, accepted definition of the meter. And it is still, as we are talking right now, it is still valid. And this is the definition as people are working on. Okay, so we know that since these are different things which we measure the distances between the buildings, between the houses, between the streets, and all different kinds of distances we measure. But some of the distances are almost standardized, because the distance between the sun and earth, it doesn't change that much, okay? So there is some average distance which we can talk, though the orbit is a little bit kind of shrinking or enlarging with the around the year. But we can still take an average value of that. Let me take another value here, which is extremely popular, which is the radius of Earth, okay? So radius of Earth in meters, it is 6 times 10 to the power 6 meters. So in short, if I say that the radius of the Earth is 6 million meters, then that's it, okay? Though when we go to a little bit more accuracies, then yes, there are a little more significant figures into that. But if you are just talking about for the approximately the height of the peak Mount Everest, you know that the Mount Everest is the tallest peak in the world. So the height of that is 9 kilometers, right? So again, these numbers are kind of approximations. Okay. When you are seeing that the exponent, which is 10 to the power something, that number, if that comes out to be positive, then means that those values the distances which we measure, they are more than meter. And when we see the power of 10 negative, it would mean that these numbers are less than meters. So these are fractional units. Okay. For example, radius of the atom. These should be definitely be fractional units because it is much smaller than the meter. And think about those approximate distances here. Well, you know that in this example, what I'm trying to emphasize, I will be trying to use imaginations a little bit. And that imaginations and suppositions will lead to a little bit incorrect results. But those results will be okay, kind of acceptable numbers. Okay, but that will be not extremely accurate to the 100%. Okay. Let's see this one. The world's largest ball of the string is about 2 meters in radius. To the nearest order of magnitude, what is the total length L of the string of the ball? Okay, there are two things going on if you think about this problem. First, there is a string, and then the string is rolled in such a way that it is creating a ball. Okay, first of all, it is given to me that the radius of the ball is 2 meters. So let me write radius of the ball R equal to 2 meters. That's the one quantity I know it for sure from the problem. Now, since the string is used to create this ball, that means that the volume of the string is equal to the volume of the ball. So the string, as we know it, normally the string is kind of a cylindrical shape because it is rounded and lengthy. But here, if you look at another problem in this, when you wrap the strings, between the strings there will be some gap, right? So if I go with the cylindrical shape of the string, then I will be comparing the two volumes of the ball and the string, which will not be matching well. So I need to go with a little bit cylindrical shape of the string. And I am supposing that the cylindrical shape of the string is such that whenever I wrap them, it's supposedly going to cover all the gaps. So there will be no gap left. Okay, so therefore I'm overestimating the volume of the string in order to account for the air bubbles inside this ball. So the string, since I took it in as a little bit rectangular shape, as you are seeing the strip, so you know that the volume of the spherical shape, if I'm going with, it is 4/3 pi r cubed. This is the equation for that. But if I'm going for this rectangular strip, then what I'm having the volume, it will be the cross-sectional area, which is there the height and the width. So that's the area times the length. So A times L. This is my second equation. And now I'm going to put them together because I'm assuming that these two volumes are the same. So 4/3 pi r cubed. Since we are going with the approximation, and you know that the value of pi is 3.1416, right? Which is a little more than 3, but since we are approximating it anyway, so therefore we can approximate this to 3 and cancel out the pi with the 3. So this is a simple form of the equation now, 4 times r, okay? Now, my concern is to determine this length. All I'm going to do is 4 times the radius of the ball, which is 2 meters, cube, divided by the area, cross-sectional area. But you know that the cross-sectional area, it is the height times width. So how should I take this height times width? Again, I'm compelled to use approximation. And for that, I'm thinking that the normal wire, it falls like around 2 millimeter or 3 millimeter. Sorry, you can actually pick any number. It could be 3, it could be 4. But for purpose now, I'm choosing 4. So when I choose 4 and I'm looking for the area of the square, it will be 4 times 4. So here I'm going to use it as a 4 millimeter square, because 4 times 4, it's giving me 40 millimeters square. And you know that here we have this millimeter, then we need to convert this to meter. Because it's a prefix, we need to convert this. So this is what you are seeing on the slides. These are the two volumes. And then when I compare and put all the values here, I get it to be the length of the string is 2 million meter. Okay, 2 times 10 to the power 6 meter.
Teacher,
Yes.
we can't see the bottom of the board.
Yeah, that's the problem with me as well. But let me remove this and begin it again, because that's a problem with me. Just. And it's not really the camera, but there is a software, and the lower bottom of the software is holding it. So let me share it again. Okay. Hopefully this time it will work. It doesn't work. There is some issue. I don't know what issue occurred, but it just recently occurred. Before this, I was teaching and it was fine. But I will clarify it later. Okay. So just work on it now. Okay. There is another question related to this, what we did, and it occurred in Major 1 exam, term 132. A hectare is a unit of area that is equal to 1 times 10 to the power 4 meters square. If water of volume 0.02 kilometer cube cover 30 hectares of flat land, find the depth of the water. I'm giving you a hint here. We know that the volume is the base area times the depth. Okay? They're asking for determine the depth. What should I do here? What will be my strategy to begin this experiment, this problem? Can you tell me?
Depth will equal to volume divided by area.
Okay, so volume divided by area, that's a very good point. But then also, if you look at that, let's put this first. Area times depth, and let's put it as a L, depth. They're asking for the depth, which is L, so the volume divided by area. Now, if you look at the volume is 0.02 kilometer cube. And when you look at the area is 30 hectares. Okay. Do you see that there is a units which are changed? Like here and there, the units are completely different, right? Okay, we need to change the units. How can we do that? The units here.
Dimensional analysis.
What is that?
The dimensional analysis. We change
turn it to meter square, I think.
Yeah, there was another thing which we discussed yesterday. There was the chain link process, which was the chain link rule. Here we have 0.02 kilometer cube, right? So here, the easiest method I'm telling you, and now you need to just be careful here when I'm explaining it. Here, inside the unit, since this cube is on both kilo and meter, both, right? So then I'm putting this kilo 1000, which is 10 to the power 3, and meter here. And inside parentheses, I'm putting a cube as well on parentheses. Okay, so when it come out of the parentheses, you know that this 3 should be multiplied with this 3. And in total, we are getting 9. So it will be this quantity times 10 to the power 9. And this will left with the meter cube. Now the second part is, please guys, turn off your microphone. There is some noise coming from you guys. Here we have 30 hectare, and you know that the 1 hectare, the area is also already given to us, which is 1.0 times 10 to the power 4 meter square. So everything is clear now. It's just a matter of calculation. You need to calculate it. So meter square will cancel with the cube here. So only 1 meter will be left to us, right? Only 1 meter will be left to us. So you already started to know that the meter is the unit of length or depth in this scenario. Now the top quantity, numerator divided by denominator, that's what you need to do. And here I'm showing you the answer. Yes.
From where did we get the 10 to the power 9?
Because there is a kilo, the kilo means 1,000, and 1,000 in the scientific notation, you can write it as 10 to the power 3. Right?
Yes.
Yeah.
Doctor, we mean a kilometer equal to 1,000 meter.
Yes, that's what we did. Yes.
You wrote 9 to power 9. Confused.
Because it was kilometer cube. That's why.
Oh, okay.
Yeah.
Okay.
Okay. So
Doctor,
yes.
will you give us in the exam how can we transfer from a unit to another unit, or
If it was unusual unit, yes, they will provide you such
like
thing.
this
But
unit,
it was-
hectares?
If it was, if like it is a hectare, so if the units of hectare discussed, so you look at this problem, this is the exam problem directly. So here already the unit conversion is already given to you. But if the units were like in normal use, like a centimeter and meter and kilometer, no, you need to know it, okay?
Yeah. Okay.
Why did we multiply the hectares by the area?
Because a hectare itself is the area, right? Hectare is the unit of area, but it was not in meter square. We wanted to convert it from the hectare to the meter square. So that's what we did. Like when you have the hectare and you need to multiply it with something which is in meter divided by hectare. So 1 hectare is given there, which is the conversion factor. The hectare will cancel out, and you will get with the unit of meter square.
Okay.
Yeah. Let's move on to the second topic, which is the time. We already know it. We don't need to spend much of the time. What is the time, right? So we already know the time. SI unit of the time is seconds. That is the standard unit. But we also talk about the time in terms of minutes, hours, days, weeks, months, years. So all these are also different units of time. So whenever we are talking about the month, we already know how long this duration is going to be. If I ask you how many days are there in a month, on the average, you will be saying 30 days. If I ask you how many days are there in 1 week, you will be saying 7 days. And then how long is 1 day? Then you can easily say that it is 24 hours. And then how long is 1 hour? It is 60 minutes. How long is 1 minute? It is 60 seconds, right? So you have all the conversion factors and all units you can easily convert from one to another. But now when we go to a little bit scientific notations and the scientific aspects of it, the time has to do 2 things. First, it has to tell us the duration, and it also has to tell us when something or event has happened. For example, if I ask you, how long is what is the duration of this class? You can say it is 50 minutes, right? So your clock can provide you that duration, 50 minutes. That's one thing. But then, when did you join this university? You can say, on Thursday, I joined this university, or Saturday, I joined this university, or 1 hour before I joined this university. So there are 2 things. One is the duration of something. For how long you have been here, the student of this university, you can say that I have been a student at this university for 1 year now. So that should define the duration. But when I ask you, when did you join this university? You can say, I joined this university in January 2019. So that is when that event has happened, okay? So if a time, anything that can give us these two aspects of the thing, then the time has to be necessarily imposed in that. Since we need the accuracy in time, and as I mentioned the example of the GPS yesterday, so we need the time with extreme accuracies, all the clocks with extreme accuracies. Like if you're running a stopwatch, in these days you will not be able to use a stopwatch which just give you hours, because that probably is useless for your purpose. So you want to have a stopwatch which can give you minutes, hours, seconds, and a fraction of seconds, okay? So that's how we want to go it. Atomic clocks, which gives us more precise time, and there are standard atomic clock which is placed at the National Institute of Standards and Technology, Boulder, in Colorado. Okay, so that's where it is located, and it is transmitted via radio signals if some people want to compare that with. Okay, so as this event has happened, the System International has formed. There were different definitions also kind of started to associate with something else. So in 1967, the standard second was defined to be taken by these many oscillations of the light emitted by cesium-133 atom. So that was one of the standardization of the second. But when we look at the things in terms of the durations, so I can give you one thing, which is the length of the day. Look at this table. There is a length of the day, and length of the day is provided you in the time interval, right? And that is in seconds. So 9 times 10 to the power 4 are 90,000 seconds. That's how long is the day. Again, when you see the power of 10 positive, it means that that duration is more than a second. When you see the power of 10 negative, it means that that duration is less than a second, okay? So here, it leads me to another thing. This is a checkpoint. I'm sending you this link. You guys go again to the chat box and submit your response when I say to do it, okay? Okay, don't begin it until I tell you to do it, okay? So that I can activate the file for you. Yeah.
Is it 10 power to 5 or power to 4 to the hectare?
Which one?
About the hectare.
Hectare? It is 10 to the power.
I just saw the hectare now 30 multiplied to 10 power 5 or 4.
4. Do you see it in this slide?
Because I'm seeing it 5. 10 power multiplied 10 power 2.
Okay, we can discuss it later. Let's move on. Okay.
Okay.
Okay. So the third thing what we want to discuss is mass. So here you guys are bringing such kind of like hectare and square meter. It is 10 to the power 4. Just check it on Google and it is 10 to the power 4. Okay. Anyway.
Okay, I know it's 4 because I see 5, but not.
Why you are seeing 5?
10 multiplied 10 power to 4. That's okay. Maybe I understand wrong. In the board, I mean. Okay.
On the board?
Yeah.
This one?
Yeah, and the 2 and 10 on the left.
This is 1.0.
Okay, it's not clear. Okay.
Okay.
It's not clear in the board.
Okay. Mass is the amount of matter that an object contains. So SI unit for the mass is kilogram, and we are very familiar with this, but oftentimes we a little bit misuse this word. And how we are misusing it, sometime if I ask you, what is your weight, right? So you are also saying you said 50 kilogram or 60 kilogram. So the weight is not actually the mass, okay? These are two different things. Weight is the force, and then we will learn it like how the weight is different than the mass later on. When you have mass, you need to multiply it with the gravity, which is 9.8 meter per second square. So the weight is actually the force that the earth apply on us. That's one thing, gravitational force. And then the mass is another thing, which is the amount of matter in an object that is called mass. So how the mass is, the story of the mass is the same as the story of the meter rod. So it also has this platinum iridium cylinder, which is kept in France, and the amount of that is accepted as 1 kilogram. And all the rest of the kilograms in the world were standardized based on that. So there are other units, like the pound is also the unit of the mass, which is also used, and we practiced on that yesterday to convert how to convert the pound from to kilogram or kilogram to the pound. So another unit, sometimes for more scientific reasons, which we were talking about the atom, called atomic mass unit, and it is standardized with the carbon 12. Since you know that all atoms have some isotopes, which will be I'm sure will be taught to you in the chemistry. So the isotopes of carbon, when you take the carbon 12 isotope, then you are taking one fraction of the carbon 12 equal to 1 atomic mass unit, and it is 1.66 times 10 to the power minus 27 kilogram. And this number, which is 1.66 times 10 to the power 27 kilogram, it is roughly equal to the mass of the proton and neutron. And in fact, neutron is a little bit heavier than this, but you can translate this for most of the reasons or practical purposes. If the high accuracy was not desired, then you can use this as the mass of proton or neutron. Here, when we are talking about the mass, different objects like the sun, the moon, and other objects that we can observe or see it, we can put the mass to it. For example, the Earth. You know that we didn't put the Earth in any spring scale or something like that, but we can use our known formulas. Based on that, we can easily determine what will be the mass of this Earth, and that is mainly coming from the gravity. And those formulas will be explained to you guys later in the chapter, probably 13 or 14 chapters. So that's where we are going into that. So some of the things which we can measure, like a grape and elephant and other things, then yes, we can put them on the spring or any other available scales, and we can measure the most accurate mass of that without actually estimating it. So mass, since we know that all objects, when it has some mass, we also know it will occupy some space, right? For example, if you look at any sphere ball, like a soccer ball, you have the soccer ball has some mass, but it also occupies a space, okay? So then we can look for the density, which is another name for this. How much mass is there per unit volume? For example, I have this duster here, and this duster has some mass and it has some volume. So when I measure the mass of this on a scale and then divide by the total volume of this duster, it will give me mass divided by volume. And the name for that is, the name for that is actually density, okay? So accordingly, since this unit is coming as the mass divided by volume, therefore the unit of it is kilogram divided by volume. So let me ask one thing. When
we can't hear you, teacher. Yes, you muted
I
yourself.
think you muted yourself.
You are muted.
We can't hear you.
Doctor, we can't hear you. You are muted.
You hear me?
Yes,
Yes,
now we
Yes,
can hear.
yes.
Yes.
One thing I can tell you that don't go to the settings and change the settings oftentimes, okay? Because once you do that, then you are unmuting me and you are trying to control, because I started to see a lot of requests. The students are kind of trying to get the control of the class. So why you should be getting the control of the class? It is creating trouble for us as well as for you guys, okay? So don't, what is that? Probably that's what has happened. Okay. So here we have this example. The copper has density 8.96 gram per centimeter cube, and the mass of the copper atom is also given here. So if the atoms are spherical and tightly packed, what is the radius of the copper atom? So we know that, we first of all know that the definition of the density is mass divided by volume. And second thing, we know that the volume of a sphere. So what is the formula for the volume of a sphere?
4/3 by then R cubed.
R cubed. Okay. So we already have, in this formula, we have the radius. And they're asking for the radius of the copper atom. So all I need to do is to put this formula here, which on the slides you are seeing that the mass divided by volume. So we are solving this for the radius, okay? So the mass, which is currently not known, but for the single atom, it is known, which is provided, it is 1.06 times 10 to the power minus 25 kilogram. That's the mass is provided. We also know the density, which is 8.96 gram per centimeter cube. The only care in this problem you need to be doing is converting the gram per centimeter cube to kilogram per meter cube. Okay, so in order to get your answer in the meter cube. So let me do this one conversion, and then we can stop right there for this topic and go on to the next one. So the density, it is 8.96 gram per centimeter cube. So how can I convert this? As I told you that since there is a gram multiplied, you want to bring the kilogram into it. So the shorter way of this is that I'm writing this as like this, centimeter cube. What I want to do is that I multiply this 1 kilogram, and how many grams are there in 1 kilogram?
1,000.
1,000. So I divide this by
1,000.
gram. So the gram will cancel out with each other. Okay. Now I left with the centimeter. So the centimeter cube, when I'm doing this, I know that there is 1 meter. In 1 meter, there are 100 centimeter. Okay. So when you are putting this conversion factor, make sure that you use the same power for the unit. So since there is power 3, the I should be using power 3 like this. Okay. So this centimeter cube cancels out. What I left with in the denominator, it will be 1 meter cube divided by 100, which I can write as 10 to the power 2, and the power 3, which is 2 times 3, will give me 6. 6. Okay? Since I have here 1,000 and I have here 10 to the power 6, so I can write the 1,000 as 10 to the power 3.
Doctor, we can't see the bottom.
We can't see the bottom of the wall.
This was the thing which I asked you at the very beginning. Can you see the bottom of the board? So your answer was
No.
yes.
Now we can see it, yeah.
Now?
It's clear now. Yes.
Yeah.
But we
Okay.
can see the top of the board by the
Okay, so then that's the conversion factor. That's how you are going to do it. Once you do this, bring this density and put in this formula. That's all the step, the complicated step in this problem is. The rest, it is quite straightforward.
Okay, Mr. Khan, how did you get 10 to the power 6?
You have 10 to 10 to the power 2 here, right? 10 to the power 2. The whole power is 3. What you get out of it? When you have 10 to the power 2 and the whole power is 3, what you get?
Yeah. Okay.
Multiply.
Doctor, can you go up a little bit? I can see the up of the board. Yes, no, okay.
Do you see this?
Yes, I wanted to see above.
Okay. Here
Okay,
you have
thank you.
power 2. Here you have 10 to the power 2. The whole is power 3. So when you are going out, then you multiply the power, right? 2 times 3. So it will be 10 to the power 6. Okay. The final thing which I want to touch, so probably we will cover in the next lecture because I may not be able to comprehensively cover this topic. I'll just leave it this topic. Do you have any question in the density part or the mass or the time? Do you have any questions in that?
Yeah, teacher.
Okay. What is the question?
I have 4 questions.
Yeah.
So, first thing, why are we learning hectare now? Like, why haven't we learned it a very long time ago?
Hectare.
Yep.
People who are dealing with, did you buy a place for your house?
Yeah.
Huh? Okay.
Yeah.
So if you are buying in the old days, then there used to be a hectare a unit. Or if you are buying like, can you afford like a larger spaces, then you will be talking about the hectare. But when you are buying for the small, like apartment or something like that, then you are talking about the meter square and something like that. So the hectare is definitely used there in the government agencies when they are talking about their measuring the whole province or something. Then they are talking about the big units in that sense.
We're going to be using hectare a lot?
We are not using hectare a lot, but once in a while, if in a question it was pop up, it will be for the purpose of guiding you to convert units from one system to another system.
Okay.
Yeah.
Another thing, do we need to memorize the discovery of the units, or is it just for the sake of the introduction?
It was for the sake of the introduction, so that I wanted to entice your interest in this topic, like how, if you attended the yesterday's class, then